Okay, let's take a second and talk about 7-8, which is regression, that idea of curve fitting, but for exponential and logarithmic models. We've done it for linear, we've done it for quadratic, we've done it for cubic. Oh my gosh, we've done it for everything. Now we're going to do it for exponential and logarithmic. What I want you to do is compare and contrast what you remember about finite differences with constant ratios. So if you don't remember what finite differences are, it might be in your best interest to go back and look at 6-9. 6-9 was where we took the time to talk about what finite differences were. So if you don't remember what they are, you may need to look it up. Now for what we're doing now, we want to look at constant ratios. Here's an example of finite differences. We took 15, subtracted negative 30. 30 subtracted 15. 34 subtracted 30, and so on. We did it the first go-round. We did it the second go-round. We did it until we got a constant value where it was always the same. And then that told us what kind of function we had. Okay? Here's an example of a different function. In this function, if we do the first difference, we get plus 0.5, plus 1, plus 2, plus 4. You can kind of start to see that we're doubling here. And if we look at the ratios between each term, if we look at the ratio of 1 to 0.5, 2 to 1, 4 to 2, and actually I could have even added 8 to 4, but I forgot. All of those ratios equal 2. 1 divided by half is 2. 2 divided by 1 is 2. 4 divided by 2 is 2. They're all 2, and since they're all equal, since the ratio between the two terms is always equal, that tells us it's exponential. It's doubling every time. It's not going up 2, it's doubling. And that's what makes this exponential. So you're going to want to look at the ratios between the terms to determine whether it's exponential. The ratios. Now, if it is exponential, we can do exponential with regression. And what we do is we do exp-reg. Now this is if you have an 84. Different calculators might be different. But when you do that for two data sets, it'll kick out all these values. This top one is the most important. It's giving you a function y equals a times b to the x. A times b to the x. Okay? And that means that the value you plug in for a and the value you plug in for b. So for this particular example, the value for a is approximately 815. The value for b is approximately 1.4. This must be a growth case. But being able to use plugging in the data and then using the regression to get the equation is something we've been working on a lot. We also need to talk quickly about logarithmic. I don't have a good example on the right-hand side. It's still in there. Your calculator usually uses natural log, and the reason it does that is because natural log is natural. It's what occurs most in nature, and occurs most in math, and occurs in science. And so we use natural log. It doesn't make a difference. It's going to give you a function the same way. It's just going to model it using natural log. The basic function for this, the parent function for this, is a plus b times ln of x. So whatever you get whatever value you get for a and whatever value you get for b is what you're going to plug in, right? Your calculator kicks out a and b, so whatever you get tells you what to plug in. So pretty basic stuff this go around. How to determine if it is exponential and then what to do after that. Okay? So we're going to practice in class. We're going to practice this part, how to determine if it's exponential or not, and then we're going to practice writing the equation. Gonna see some word problems, so fire up for that.